second year we've had an event out here at the Peace Farm, and the folks out here are really accommodating. Josh Slotnick, who kind of runs this place, he's an amazing person. He called me up, I got a phone message, he's calling me at 3 o'clock, he goes, Dave, what were we going to do for you? What kind of setup did we have? And he's out here trying to make salads for us, because he had forgotten. So, what's that?
Yeah, salads are delicious.
The salads, and most of the food, I believe we asked Bob, who knows Josh, to include as much of the food as he could from the Peace Farm, and I think he did. And also the ice cream was Huckleberry, and it came from, how many of you have been to the Big Dipper so far? All right, so you've discovered one of our important places in Missoula. So we're really thankful to the Peace Farm folks in this beautiful setting. I don't know, I just really enjoy being out here, and it's just a peaceful, good place. And so thank you to them. And for some of you, if you didn't know, there's a couple of groups here that are, we're working with. Is the National Science Foundation is one of our sponsors, and they brought 28 graduate students from around the country to think about the larger social and ethical dimensions of scientific research. And they've been focusing on 3 groups: nanotechnology, agricultural biotechnology, and climate change. And today was our climate change day, so we had a good day. And also, Andrew Light here is teaching again an environmental ethics institute, so we have several students here for that, which is, so we're glad to have them here. Also, we have Royce Eastrom, the provost, who's around here. There he is, and we're really glad for that. And the really thing that's really great about the provost is I saw him at the Steve Earle concert the other night. So we thank him for coming. I know this dog, it's really nice. So now to our speaker. And I knew Dick Manning was in town because I was sort of peripherally aware of his work and the kind of writing he did. And a few semesters ago I taught an agriculture and environmental ethics course, and one of the assignments was to pick a book on the general topic and read it. And one of the students picked Food's Frontier, which Dick wrote several years ago. And it's a really interesting book. The McKnight Foundation sponsored Dick, and he went around and looked at different kinds of ways of doing agricultural research around the world. And I thought this was a really fascinating book, and the class had a really nice discussion about research and what people need around the world to make agriculture work. And I go, I got to get to know this guy. He's in town and he's writing these interesting books. So I just called him up and we got together, and we've been having some really good conversations since. And I think he's a real resource for someone like me who's into these issues to have him here in Missoula. He is a journalist, and you've been listening to a lot of scientists, but he knows a lot what the scientists are up to. And some of his books, Against the Grain, How Agriculture Has Hijacked Civilization, and Inside Passage, a book that I just was talking about the Northwest, and the book that that got me interested in what Dick had to say, Food's Frontier. And in, I believe, Against the Grain, there's Michael Pollan writes a small bit about recommending the book, and it said, it's radical in the best sense of the word. And I think his title, you can tell, you're going to look at things a little bit differently when Dick comes up and starts talking, especially how biotech takes us to the wild side. And so welcome to Dick Manning.
Thank you all for coming. It's a nice summer evening, and I'll try to bear that in mind and not go on too long. It's a pleasure to be here literally in my neighborhood talking. I've talked about these issues all over the world, and this is by far and away the most intimate setting, at least in terms of my thought. In fact, it's more local than you might think, in that, like most writers, I chain myself to the keyboard every morning for about 2 hours. And then when I'm done, like most writers, I take my spaniel dogs for a walk. And that turns out to be the most productive part of the day, of course, when I walk with the dogs. And my walk every morning is right down those trees, right there down that path. So if I get stuck here and start gazing off into those trees, I'm looking for thought balloons that got snagged up there, and maybe I can pull something out of it. About 94, 95, I did a fellowship at Stanford. And I got to know some people surrounding Paul Ehrlich there in the conservation biology community. And those people were worried about the environment poverty, food, agriculture, all those issues. And it started me really on a trail that I haven't left since. I'm still writing about those issues and have been. During the course of that, I worked with the McKnight Foundation, as Dane mentioned here. I worked a lot in the American Midwest. I worked with the Rockefeller Foundation and did a profile of something like 12 or 13 programs on biotechnology and rice. And have written a lot about biotechnology, been around the world in something like, I don't know, 25, 30 different countries, talking to scientists and farmers about what goes on. And as a result of that, I've thought a lot about the issue and have assembled a kind of a viewpoint, a long arc of thinking that I'll try to cover tonight a little bit. And don't expect to get a lot of information out of this. I mean, this is mostly, I'm here to kind of expand thinking a little bit and just poke the edges of how we think out, especially in the area of biotechnology, because people have a very narrow view of biotechnology. By the same token, I'm kind of embarrassed to just be talking about technology, because having spent all this time looking at developing world agriculture, the environment, and poverty, I come away thinking that we spend way too much time talking about technology. And in fact, if the developing world could somehow get a hold of the technologies that exist today, they'd be a lot better off. And very often the problems there are the fact that we impose technology in inappropriate social structures, and most of the work has to be done socially. And when I think about things like appropriate technology, I think about the cell phone. I was in Africa last year and did quite a bit of work there and was astounded to see how Africa's social system is being revolutionized by the cell phone, for the better. A lot of good things are happening as a result. So that's an example of, when we think about university level technology and the kind of thing that goes on, that kind of research, generally that's really not what's necessary. Having said that, though, there's a place for it. But I want to put that place in context if I can. Dane mentioned my book about how agriculture hijacks civilization, and I'm fairly radical about this whole thing in that I believe there is no such thing as sustainable agriculture. It does not exist. Okay? And what I'm talking about can be illustrated very cleanly right here. Anytime you're in a farm, you can always talk about these issues by pointing here, here, and here, because the issues are all right in front of you. But you see this nice diverse group of crops out here and people eating good food and all that stuff, and that's a good thing. But if I were to draw your attention to anything, I'd draw your attention to the fence that's all the way around these fields. Okay? That fence has to exist here, otherwise those crops would be gone in one night because of the deer that are just on the other edge of it right now. There are about 20 of them up there with spotted fawns, if you're into that sort of thing. That fence to me is what's important, because as long as we keep the wild on the outside and the domestic on the inside, and we're not able to bring those two things together, we are screwed. Okay? And that's the fundamental flaw with our agriculture. So what interests me is revolutionizing agriculture and remaking all of agriculture in a wild image. How do we get back to something that is fundamentally sustainable? The worst mistake humanity ever made was domestication of wheat, which occurred about 10,000 years ago. Okay? Wheat, rice, corn, all of those things are annual grasses, and they're biological freaks. And what we have to do to grow those biological freaks is depleting our soil and depleting now our natural resources, energy, and daily putting carbon dioxide into the atmosphere and contributing to global warming. And it has degraded humanity for 10,000 years. Now, having said that, once you've been around the world and once you visit poor people on the countryside and understand people are starving today, then you can back off your kind of revolutionary thoughts about remaking agriculture and say, okay, we can take a few Band-Aids here, folks, right? What can we do today to make conditions better? So I'm always interested in things on two different levels. Not interested in cats. On two different levels. One is what's appropriate in getting us through the next couple of weeks. And literally so in the developing world. What's appropriate to stopping the degrading sort of poverty that's grinding through Africa, the Middle East, South Asia, and making those lives better tomorrow, that kind of urgency. What's appropriate in making places like this doable? But also, what do we need to think of in terms of completely revolutionizing agriculture and rebuilding it from the ground up? and bringing the wild systems back into it. That's what interests me the most. So I'm always thinking on those two levels, and I'm going to try to bring both of those back to biotechnology. Because I'm a journalist, I don't talk a lot about facts and theories and things like that. I talk about characters. We go around looking for characters. That's what makes our story. So I'll string together a series of characters here for you. My first character is Susan McCooch. She's an interesting woman. She's probably my age, relatively close. She is now a molecular biologist. I don't think she'd call herself that, probably a plant pathologist. She works at Cornell. She started out in the business as a radical, quite literally. When she was when she was a young woman in her 30s, when she was fluent in Spanish, and she traveled through South America and became completely radicalized, to the point that she hung around with some people, got thrown in prison. And she got involved in the politics of the time. So she rethought her life at that time because her friends were being killed. And she said, what do I do for the poor people? Well, her answer, what do I do for poor people, is I get a degree in plant pathology. Because if you can deal with farming and the problems of plant diseases, you can help poor people. So she came back to the States and did that. Applied for graduate school at Cornell and was rejected because she was had a child and was married. And so they finally took her as a provisional graduate student. So she would have to prove herself. She was on probation. And at the time, gene jocks were just getting going. This was in the 80s. And so genetic engineering was all the cool thing, and people were starting to do that. And she worked in Steve Tanksley's lab there. And he was doing all the hotshot genetic engineering work. And they had one project that the Rockefeller Foundation had asked them to do, which was mapping the rice genome. And all the hotshot PhD candidates turned it down. Said, we're not going to do this. This is a loser. This is dead end. Rice is an orphan crop. There's no money in it. And it was true. There was no money in it. So McCooch, the provisional student, took it on and quickly learned the Japanese had spent $5 million trying to map the rice genome and were unable to do it. Okay? But she was going to do it anyhow. And she succeeded. As a provisional graduate student, she was able to map the rice genome. She beat Syngenta to the punch. Not only did she beat Syngenta, and they were interested in patenting the rice genome so they could own some of the intellectual property rights to what was learned from there. Not only did she succeed, she did so and posted everything on the internet right away. So created this vast worldwide network of people who were plugged into the rice genome right away. Well, mapping the rice genome is kind of like preparing the outline of a novel. Once you begin to understand that, you begin to understand how rice works to a huge degree. So almost immediately, one person, a woman named Pam Ronald, went out from that particular lab and was able to genetically engineer, isolate a gene for resistance to bacterial blight in rice and genetically engineer that into rice right away. So there was this almost immediate success. I'll tell you why I bring that up later, but let me go on with the story a little bit. Because now I brought up biotechnology and I brought up genetic engineering, and that's misdirection at this point. Whenever we do these discussions now, people think as soon as I say biotechnology, I'm talking about genetic engineering, and I'm not. Okay? So that's a subset of biotechnology. It's very important in public science. And what I work with is public science as opposed to corporate science that goes on in Monsanto, Syngenta, the stuff you've heard about and debated ad nauseum at this point. Public science is interested in an entire range of biotechnology tools. And those include a marker-assisted selection. All that is DNA fingerprinting that when you do plant breeding, you are able to tell if you've been successful by looking for a marker for that gene, marker-assisted selection. They do something called embryo rescue, and there are a variety of techniques. But basically, when you do wide crosses, the embryos aren't viable. And so you have to have all these heroic techniques to rescue that embryo so you can make a seed out of it. It allows very wide cross hybrids out of the deal. They're interested in functional genomics, which is we just want a big old map of the genome so we can see what's going on. Now, part of that does indeed enable genetic engineering. But there's a reason I'm bringing all of this up, because all of the negative baggage of biotechnology attaches to genetic engineering. And that's getting all the attention because of intellectual property right issues and social control issues, all those things. But it turns out that as we look at these other quieter branches of the science out there, that not only are they appropriate technology, they're actually highly effective. And in the end, we can do everything we could do with genetic engineering with those other technologies. And that's what's generally. So, for instance, there's Pam Ronald's genetic engineering of a resistance to a rice disease in rice. Okay. That was subsequently repeated through traditional breeding. So we just crossed two rice plants. They had that resistance like that. They were able to determine it with a marker, genetic marker. You didn't need the genetic engineering to begin with. That's kind of a side issue to this, but it's important, and I'll tell you why in a second. But I want to go on with a couple more stories here. Okay, now we got the rice genome mapped, and this is in 1988 that this occurred, and so through the 80s people were starting to think now where the next step is sequencing the genome. So if you have a map of a genome, that's very much like the outline of a novel. Sequencing the genome is having every single letter of the novel printed down, and that's where we were headed. But all this was happening simultaneously with some other work on other genomes, wheat, some of the other grasses, some of the orphan crops like teff, which is raised in Ethiopia. Because basically humans are seed eaters. We get something like 70% of our nutrition from the seeds of wild grasses, annual grasses, wheat, corn, rice, and that group, those three. At any rate, people were thinking a lot about these things, and they were doing separate branches of research in each. But as they got into it, and this was a shock to everybody that was involved, because wheat has this fairly small, compact genome, and corn has one that's like an order of magnitude larger. It's enormous, just huge number of genes, and rice is somewhere in between. Well, a guy named Mike Gale, working in Britain, was taking a look at this whole thing. And if you think about a genome, all it is a big long stretch of DNA with the A's, the C's, the T's, and the H's all written out on it. What he did was start to form that into a circle. And if you took the white genome, which is small, it would go in this circle. And then if you took rice, and I'm making this up, but this is close, bigger, it would be a bigger circle. And corn was a bigger circle still. So he did that, superimposed those three circles, and started twisting them a little bit. Say, we know this gene for this trait, say dwarfing, is here on the corn genome, it's here on the wheat, and it's here on the rice. So what if we twisted all three of those so they lined up? So that gene is now lined up in that circle, like a roulette wheel. And as soon as he did that, they figured out that he could take any spoke on that wheel and find the genes for those, for the same trait. So if there's a gene for yellow, it went out one spoke of that wheel. And that led to something called synteny. What that told us was that nature really doesn't waste a lot of time reinventing the wheel. And so although the genomes are very large or very huge variations in them, they had the same tricks over and over again. They did the same thing. And that little piece of wisdom all of a sudden revolutionized the way we thought about crops. But because of all the work that had been done in wheat and corn before, and those are the big money crops, wheat and corn, that's where all the money is spent, we could suddenly take that knowledge and put it to work not only in rice, which at the time was an orphan crop, but in teff, in barley, in millet, all the other grasses that had been neglected. So all of a sudden scientists were finding things like bang, 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 like that, because of that one quick realization that we could do those things. Where this comes in, and why this is really important, is because of the fact that all the big money crops have taken all the research. And so now there's something out there called orphan crops, right? There are things that nobody paid any attention to, but they're in fact what the world eats. So if you go to Africa, and people are concerned with sweet potatoes and cassava and a number of things that had not been researched. And in fact, nobody wanted to research them because they thought, hey, do we have to do 40 years of work to get to the point where we can do these well when we already know how to grow corn? So what they did was go to Africa and say, you guys grow corn, because we know how to do that. right? Nutritionally, that was a bad deal. It had all sorts of disease problems. It was the one-size-fits-all approach of industrial agriculture. And all of a sudden, we could subvert that. One subversive move. We could say, this knowledge that we have out of this genome allows us to apply all of this science to these orphan crops. And we can do this work in orphan crops. Not only that, we have this technology called marker-assisted selection, which allows us to do that literally in field stations this size. So I've been in many field stations that would look about like this, and they're growing out the stuff here, and there's a guy who did his PhD at Cornell, and he's in a shack like this, literally a shack in many cases, doing marker-assisted selection, often even doing genetic engineering. I've seen genetic engineering done in rooms this size. Okay? So it becomes appropriate technology because it can become local. I want to kind of illustrate that one now with another story. And in my time, I'm not going to have time to read, but I had a chapter I wanted to read here, but I'm not going to. I'll tell you the story instead. Let's go back to rice. Okay? And the guy who's doing this, his name is H.E. Shashidhar. And his laboratory is in Bangalore, India. And I visited him one day there to see what kind of work he was doing. And it was a great laboratory. It was in a stone building with not very good windows in the second floor. And every day at 4 o'clock, the monkeys would come in and raid the laboratory. And they would come in and raid because every day at 4 o'clock, all the instructors left. When the instructors left, the graduate students would feed the monkeys. And so the monkeys had figured this out, and they all showed up that day at 4. So I saw the monkeys, and then we went visiting farmers. But Shashidhar was working with some fairly prosperous farmers around Bangalore. And Bangalore is kind of the Silicon Valley of India. So there's enough money floating around there that people can afford nice vegetables, and they pay well for food. So operations like this do exist, and the markets exist in India to do that. But there are also very poor people living around India, and that's who Shashidhar was working with. And these people were growing rice. But they weren't growing the rice you think of. So, as soon as you think of rice, you think of paddy fields, right? Flood irrigation and plants growing underwater. And while it's true that the majority of the rice in the world that we eat grows in paddy fields, the majority of the acreage of rice is planted to dryland rice, no irrigation. And it's dryland because the world's poorest people have it. They don't have access to irrigation or water, so they have to grow dryland rice. And so when the Green Revolution happened, the researchers from IRRI, and that's the International Rice Research Institute, which is based in the Philippines, that's the institutionalization of the Green Revolution. Those researchers went to these farmers, these very farmers, and said, no problem, we got these improved varieties here that we've bred out for irrigated rice. You grow these and you're going to be fine. Well, they did grow those, and their kids starved to death because their yields were much lower with the dryland rice, but they could get a yield every year. They wouldn't lose a crop. Where with the improved varieties, they would lose their crop. So, and they knew that. The farmers knew that, and most of them didn't grow it, as a matter of fact. They continued to grow their land races. So here you have that classic clash of industrial farming and the Green Revolution and local agriculture. Well, Shashidhar came into this whole situation with DNA fingerprinting. So he was going to do marker-assisted selection. And what he did was do genetic markers on every one of the land races that was being grown. So he'd go out to the local farmer and say, what do you grow here? Well, we grow this one because on this particular patch, it usually survives the drought. Plus, it's got this nice orange color we like a lot, and people like to eat it in this particular dish. So we'll go with that. So he found in that area around Bangalore, he found 500 varieties of rice by doing DNA fingerprinting. Okay, he's using biotech at this point, folks. That's DNA fingerprinting. It's sophisticated stuff. He has gone out and he has proven that there are 500 varieties because he's got the genetic fingerprints to tell you that. Not only that, he knows which the best ones are. And he can find the gene that marks a given trait for that. And he knows the disease problems that were happening in that area as a result of rice diseases. So now he gets on the internet and he says, okay, who out there has got a variety that's resistant to this disease? He brings that variety back in, he gives it to the farmers, they do a cross-breeding program. He uses genetic markers to say, okay, we got all your traits there and we got the disease resistant because we were able to prove that with biotechnology. And he solved a lot of problems for a lot of people. That's biotech at work locally on those kind of Band-Aid solutions. Okay. I'm going to fast forward a little bit now. This is, maybe 6, 7 years ago. God, it's probably longer than that. I was in Beijing. And this is well after I'd met Susan McCooch and after I knew the story. And I started talking about Susan McCooch, right? We're in Beijing for the International Rice Conference. So it's all the rice scientists in the whole damn world are showing up there. And the president of China is speaking that day, literally. So it's a big deal. Rice is a very big deal in Asia. And when they have scientists show up, everybody goes to listen to them. Then McCooch shows up, right? And she's a rock star in this group. She's a rock star. Everybody knows who she is. They know her story. And she's literally mobbed in the hallways. People are, autographs, straight down to autographs, because of what she had done for rice. But what she had really done, everybody recognized her for mapping the rice genome. What she had really done was showing up that day when a group of Chinese scientists brought a poster to her. And it was their research, and it was based on her research. And basically what they had done was a very simple experiment. They had crossed China's best yielding rice hybrid. Okay, so this is their super rice, the best thing they've gotten. The Chinese have good rice. They crossed the best rice with a wild relative of rice. And they got a 30% increase in yield. 30%. That's astronomical. That's the kind of thing you don't get. Now, you need to think about this in terms of just gross, crass dollars. Okay? 30% increase in the world's most important crop. What's that worth in dollars and cents? Now, what was it worth to preserve the biodiversity that kept that wild relative of rice alive? That was the point. Because it was because they had access to those genetic traits in that wild relative, they were able to get that phenomenal yield increase. But there's more to it than that. And this becomes a theme that I see over and over and over again. That now that we understand the genome of rice and all these other crops, every scientist I talk to in the field keeps talking about wild relatives. Okay. An example, if there are beets growing in this field, there are undoubtedly beets growing in this field. They were bred by Erwin Goldman. He's at University of Wisconsin at Madison. You guys seen golden beets? The yellow ones? Okay, that's Erwin. You've seen the striped ones that are red and white through? Seen those? That's Erwin. Okay, he bred those beets. What he figured out is that there are 2 genes for red in beets. Okay, and by turning one of them off, he made golden beets. But he found out that by turning them both off, he could turn them off in layers, off and on, off and on. He's not doing genetic engineering, he's just stopping gene expression at this point. That beets played out or grow in layers, so he could do the gene so it switched on and off as it came out the layers, and that's how he made the red and white striped beet. And it sounds like a cheap parlor trick, right? Well, the thing that makes red color in beets is a powerful anti-carcinogen. It's a cancer-fighting agent. Okay? And so he did this because he figured if he could make beets attractive like this, he would increase consumption of beets in the U.S., which is exactly what he did. And so now people are eating their beets because they're good for them, right? And they're fighting cancer because they got better red stuff in them. Cool. Now, what Erwin told me is that he's an onion breeder, a beet breeder, and one other thing, I think carrots. And he's the only one in the United States. The only breeder, because that's an orphan crop. We have orphan crops in the United States. What he told me is that 10 years ago, it would have taken him forever to figure that out and to do it. But now, with functional genomics, he has the tool to go to the gene banks and treat it very much like a card catalog, that he can go through there and find the genes he's after almost immediately and breed those in. And those genes invariably come from wild relatives. So if you go to Mexico, for instance, where the largest gene bank is of corn and wheat, you'll find every wild relative of wheat possible there. And there they've sat in refrigerators for 40 years. And there's something like 300,000 accessions, 300,000 different varieties, right? They've sat there because nobody can figure out what to do with them. because to find out what they're capable of doing, you have to grow them out. But with genomics, they're able to go in and pick those genes out right away and understand exactly what they've got. What all this raises is this ability to go back to the wild and redo domestication. Okay? Because invariably, these plants are not annual grasses that we grow, they are perennials. Okay? And that's the line of distinction there. The problem with agriculture is we grow annuals. And because we grow freaks, biological freaks, wheat, corn, and rice, we have to plow the soil every year. We have to reseed them every year. They deplete the soil, and they take carbon and put it in the atmosphere. So if you go to a prairie soil in the American Midwest, it has something, before white settlement, it had something like 12% organic content. It now has about 5% organic content. That's a result of growing annual grasses on it. All of that organic content decayed and escaped as carbon dioxide into the atmosphere. Most of it. If we're to reinvent agriculture, then it won't look like this. This is not all that much better. I mean, yeah, this is a nice, diverse farm, but we've probably got, 15 varieties of vegetables out here and probably 4 or 5 different species represented. That hillside probably has 200 species of plants on it. Okay? That's what native systems look like. But if we're to reinvent this, then we have to do it with perennials and figure out how we engineer, and this is what Wes Jackson, everybody heard of Wes Jackson? I need to go into that, or I can talk about Wes Jackson's work. Essentially what he's trying to do is reinvent agriculture to look like the prairie. So it's a diverse, it's a polyculture of perennial plants instead of a monoculture of annual plants. Okay? That's where we need to get. What has happened is biotechnology has given us the tools to do that. And in part to do so by recovering wild genes, by going back and appreciating what was there to begin with. The process of domestication is really pretty distinct, and it's a very powerful process. People worry a whole lot about genetic engineering, but domestication was just simple selection pressure that radically changed a number of species on the planet. I always tell people to think of this in terms of that Chihuahua lapdog you see down at the shopping center sometime. That's a wolf. Okay? That is genetically identical to a wolf. And the only difference is selection pressure, human-caused selection pressure on that animal, domestication. But if you look at the domestication of plants, it's not really change. We can be more specific than that. There's a theme to it. It's a narrowing. So if you look at the genomes of wild plants and wild relatives of, say, rice, they're very broad, they're big. And all we're doing is knocking out genes we don't like and having what's left. The best example of that is color. If you go look at wild rice growing, and I've done this, in fact, wild rice is the leading weed in Central American rice fields. So it's kind of interesting, but it's brown, it's red, it's black, it's every color you can imagine. There was a conscious effort to breed all colors out of rice, going back 10,000 years. The Chinese considered that you were a barbarian if you ate colored rice of any sort. The rice needed to be white. And so slowly through the breeding process we get it out. Well, the colors in rice all encode anthocyanins, right? Which not only ward off insects and diseases, but also cancer. So all of those things were in there. All of those traits we want today of stopping disease in plants, stopping disease in us, increasing our nutrition, they're all there in the wild plants, and we kept knocking them out. That's a general theme, that we can recover those. All of this that I'm talking about, though, or most of it, speaks to that kind of Band-Aid I mentioned earlier. That I'm thinking about the Band-Aids. How do we make the agriculture we're doing better, except for the re-engineering? But I want to leave this all with another point. One of the things that genomics finally taught, and there's something else going on in genomics. I mentioned marker-assisted selection and a number of other techniques. But one of the things happening now is something called microarrays. They're kind of cool. I first saw them at work in Australia, and it basically, if you could imagine a flat-screen television with its many, many pixels, and one of those pixels would light up each time a gene was expressed, you would have a microarray. That's basically what it looks like. So we don't have a static picture of the genome any longer. We have a picture, and so you could take, for instance, the gene of rice and attack it with rice blast, which is a rice disease, and then watch that flat screen and see what it does, and then see what different kinds do. Not only can you do that at the species level, you can do that at the ecosystem level. So you can take an entire diverse ecosystem of its thousands and thousands of species and watch individual genes react to individual things within that system. It is mind-boggling. It's complexity. It's chaos. It's all those wonderful things that nature is and we are not. Okay. And if you speak with a scientist who have done these experiments, who tool around with this level of the science, you're going to find some fairly interesting people, especially over a couple bottles of wine late into the night. You get some fairly interesting discussions. What you will invariably find is a lot of humility, a lot of understanding of how little we appreciate what's going on. I liken this to, if we were to think about the early experiments in genetic engineering, the kind of things we talk about in the press now or in public debate and so forth, they're really like a child, a 5-year-old child's stick man drawing of God. That's how far they miss the mark of appreciating. It's like understanding where the light switches are in a cathedral and saying you understand that cathedral. You understand almost nothing, because nature has solved every problem that ever existed. Okay? That's what evolution is. It's species reacting to problems, solving those problems through mutations, through new sets of genes, through genetic solutions, and then recording those solutions in the genome itself. That's what a genome is. Okay? It's not a light switch. It's not even a computer. It's been likened to. It's a cathedral. You walk into any genome, you can take the genome of that sunflower and go in and you're in a cathedral. You're in a library. You're in this vast library of information that encodes every bit of history that plant ever went through, forever. You can almost see the worn spots on the floor through history. You can look at the genome of wild rice in Latin America and you can tell the story of slavery, literally true. You can tell the fact that if you walk into the villages around there, you're going to hear a 5-tone pentatonic scale and blues music because of the genes of those rice, because they're African. Those things are all encoded in there. It's that level of appreciation that biotechnology can give us and is giving us. A sense of humility, a sense of how incredibly complex nature is, and also some of the tools to manage complexity. The problem with industrial farming and the way we grow our food today is it's reductionist. We simplify everything to an industrial model of input, throughput, output, as opposed to understanding that we live in ecosystems. And ecosystems are complex, chaotic, and unmanageable inherently. And so ultimately what I hope biotech can do is bring us up to a solid view of the genome and understanding just how squishy and how chaotic and how crazy it is to understand that what we have is worth conserving, the wild genes. It's a basis of conservation that we must manage, but as we manage, we have to appreciate complexity and chaos and approach nature with a sense of humility. I've covered way too much ground, I'm afraid, but maybe not. But I can take some questions here if you folks are of a mind to throw them at me.
Let's thank you first.
So I think about the end of your talk, you said this phrase which maybe I think is quite important. So you said that in the nature already found the answers to all the questions through the process of evolution, which I So first, I think that this is not entirely correct because evolution is a process, so it's always ongoing. So and its intention is always finding the answers to the questions that are out there. It hasn't yet found the answers to the questions that have not been asked yet. This is one thing, and the other thing is that we as humans, we cannot always wait for the nature, for the evolution to take place, because it takes a long time. So we want to manage, we want to control, we want to engineer so that things keep in pace with our development. And that is why we have domesticated the wheat, that is why we're now engineering the plants. And so because sometimes that makes things faster than just crossbreeding.
Everybody hear that? Yeah, and that's right. Let me respond with a couple things. One is, one of the things that has occurred within biotechnologists and agronomists and so forth is a distinction between in situ and ex situ conservation. What in situ or ex situ means is that you go gather the seed or whatever and you put it in a freezer someplace, and you've done the conservation. What in situ means is, we had talked about the land races of rice. It means that you make sure that as many as those species of rice stay out there in the field, with those farmers' field. What that is a recognition of exactly what you said, that evolution is a process. And you cannot conserve biodiversity by putting in a freezer. You do the in situ conservation in sight, so that process continues to create. So there is a recognition of what you talk about. Second point I want to respond to, and while agreeing with what you say, is that you said evolution happens slowly. Human evolution does, but evolution happens very rapidly. And in a lot of cases, bugs, for instance, that's all that pathogen or disease resistance is all about, or resistance to insecticides, for instance. So you throw an insecticide out there in 2 generations, the bugs are resistant to it. That's evolution at work, and forced evolution. That's a form of domestication. So evolution is happening all the time around us. It's happened in many, many forms. And the kind of the record that is accrued over the last 15 or 20 years of looking is every time a scientist looks to solve a problem, especially disease resistance, drought resistance, any number of things, they'll find a plant that's already solved it someplace. And it's a question of getting those diseases. So that's what I mean when I say evolution has really solved all the problems. It has solved all the problems that have existed until now. If you're a plant, one of your relatives faced that problem at some time. And so that's been solved and written out in the genome. Are there problems in the future? Sure. Yeah, now I'm talking about deliberate re-engineering all of agriculture? You bet. Yeah, that's not evolutionary. That's something we're going to guide through cultural evolution. Yeah, and that's why I'm hoping we have the wisdom to do that. Yes.
How do you see property rights kind of playing into your ideas, both intellectual property rights and actual physical property rights, if we're going to be blurring the line a little bit between the wild and the domestic?
Oh God, we can carry on about this for days. Intellectual property rights was a key issue in genetic engineering. That's really what stopped it from happening. So a bunch of companies, especially Syngenta, corralled a whole bunch of patents on things, some of which had been done in public institutions with public money, and they patented those genes. And a bunch of judges gave them broad patenting rights on things that they shouldn't have had a right to. There is a very active subversive movement alive within the community of scientists I'm talking about. And basically, there's a guy named Richard Jefferson. He works at an institution called Cambia in Australia. And he's doing something called open source biotechnology, which is completely analogous to the Unix system, right, the computer system. So people write it and they post it as soon as they get it. Susan McCooch did the sequencing of the rice genome by a series of laboratories all over the world. As soon as they got a little piece of the puzzle, they'd post it on the internet one day. So they made it public as soon as they possibly could. That was deliberately subversive. Syngenta fought them as they were doing this, and they said, screw you, we're doing it anyhow, and kept posting them. Finally, Syngenta started posting its results with them. So it is a problem, but it's being subverted, it's being wired around. with some. Now, the other issue is of property rights, as in literal real estate property rights, is just every bit as important. And one of the problems in the developing world is that that's the social issue. Remember I said that these are not technological, they're social? People don't own property, or they can't own property, the laws are really vague and loose and all those things. And as a result of that, they can't have this kind of rational approach. So that's one of the necessary social institutions, private property. Yeah, we need to so there are grazing systems that cross over, for instance. There are systems of the commons. Last year I was working with Maasai people in Africa, and they were working out a common system so they could, because private property was really subverting what they did, which was grazing. And so that's a huge issue, but there's no easy answer on it. But all plays into this, and certainly private property is the social institution.
So climate change is another topic that we've been talking about here this week. It obviously affects agriculture. So I'm just curious what your travels have shown you about what kind of radical changes that's going to force in agriculture.
Yeah, I think about climate change a lot. And it's interesting to see that debate within the circles of people who do this research. Because 15 years ago, there'd always be somebody who stood up at the seminar and said, yeah, and then there's climate change, and everybody go, yeah, and then they go back to whatever they were doing, right? And it's not because they didn't believe it, it's because it was unthinkable. It was unthinkable, the kind of level of change because it's like everything that they had thought through and worked for and planned was going to fall apart. That's particularly acute in sub-Saharan Africa, which is the worst problem in the world right now. What do we do in sub-Saharan Africa? Well, that's where the drought's going to be the worst. The climate models are pretty clear on that. What is marginal there now is going to become more marginal much more rapidly. And then you have things like, and I think about this a lot because if I were to characterize the last 20 years or 15 years of people thinking about this, and I could see them all going up to the front with their PowerPoints doing the line on the graph. And you've seen them all, you name it, they've done it. And you've seen all the graphs. And they all had fairly linear extensions. They didn't get that exponential that fast. Everybody was relatively hopeful, saying, okay, yeah, we got some bad problems out there, we're going to deal with them. Here's how, and lay out the 20 years. Nobody saw this year coming. Nobody saw this year. With the food prices doing what they did this year, it's been astronomical. Over the top with oil prices, and that's that's climate change. That's Australia losing its wheat crop that started this whole ball rolling, and it was people keep calling it a perfect storm, and that's about right. So the extrapolators, the predictors, the ag economists, they're all been blindsided by what's happening in the last couple of years, and people have not done the kind of tipping point analysis that I think is necessary. That I think it's going to be one hell of a lot worse than anybody predicted. And it's because of climate change.
Picking up on that, does this imply there's a way to grow crops without pesticides? And a lot of there's a huge carbon footprint with pesticides. So
Yeah. I mean, the short answer to that was genetic engineering in a lot of places. I mean, BT Cotton did an enormous amount to reduce the pesticide load in China, for instance, and that's pretty well documented. So. But that's another stopgap short-term answer. And the biggest problem with pest to begin with is the monoculture. That because we do this monoculture and because we grow only one thing, there's this big old glowing light for any pest that's coming along. And now, we're not going to get rid of the monoculture tomorrow, but a lot of what's happening with marker-assisted selection and the breeding I was talking about is related directly to pest resistance. And so there have been some pretty durable resistance paths bred into some plants, especially for some insects, some diseases. So there's been some pretty good success in that. And then there's been a lot of work on integrated pest management in the developing world. In the developing world, this gets traction a lot faster than you might think because of the cost of the inputs.
And I was also thinking fertilizer. Actually, fertilizer is a bigger one.
Yeah, and fertilizer was the Green Revolution solution. I mean, let's do that. And if you look, over the last couple of years, the Gates Foundation has looked how it's going to spend its multi-jillions in Africa. And they're essentially going, from everything I've heard, repeating the Green Revolution stuff about fertilizer. Well, in some places that's a pretty good answer. There's something at work in all of developing world agriculture, right? It's the hammer principle. Right? You've all heard the hammer principle. Once you invent the hammer, everything looks like a nail. Right? Fertilizer. That's the hammer. And so everything looks like a fertilizer problem out there, and there are others. But there's been some pretty good work. For instance, I worked in a project with FAO last year saying that if you subsidize fertilizer in a given country, and that was been the prescription, especially in World Bank like that, if you subsidize fertilizer, you will create income inequity. You're going to make rich farmers and poor farmers. And so people are moving away from that a bit. So yeah, there's this, but the whole input model is still out there. The hammer principle is still alive and well, thank you, in the world. And there's a tension. People are working against it, but it ain't going to go away tomorrow. Nor should it. I mean, in some areas, fertilizer work real well.
Dick, I've got a question about the social aspect of this change, because you've talked a lot about the biotechnology, but you've mentioned that there is a social need, that social changes need to be made. We were at the Fish, Wildlife, and Parks Commissioners meeting a couple days ago in Helena, and they were discussing the easement for a ranch, a conservation easement for a ranch out in Valley County. And one of the commissioners expressed concern about the state getting this conservation easement because he thought there was some sort of pressure to turn eastern Montana into a Serengeti. And seems to me you're kind of talking about this sort of this rewilding of agriculture. And the thing that shocked us, or shocked me anyway, was the Fish, Wildlife, and Parks employee said, "Oh, absolutely, we do not want a Buffalo Commons."
Yeah, and I'm engaged in that right now. I just finished a book that University of California Press will do next year about rewilding the West. And it's about a project in central Montana about putting bison back on the land.
So how do we, I mean, the bioengineering seems simple compared with the social engineering.
Yeah, and it's not really social engineering. It's just like anything else. You start making money at it and they'll come along. And so what my argument is that one of the reasons we need to look at wild systems and respect them is because they're more productive. More productive in the sense of biomass, more productive bottom line, profits, because they're taking care of their own inputs. So bison on the landscape put on a hell of a lot more protein than the cattle do today because of the way they grazed and so forth. And so it's that kind of demonstration that needs to happen. I was just in Iowa 2 weeks ago spending time with guys doing grass-fed beef. And what they were doing was converting Iowa corn land to permanent pasture, which is a little bit like saying you were going to put a nuclear waste dump in Missoula. It'd be about every bit as politically popular, but that's what they were doing. And they were making more money than the corn farmers by doing it. And it was that fact that was going to pull that along and really bring that biodiversity back into that place that desperately needs it. And it's the same thing here, that we're going to demonstrate some systems, the kind of over-yielding that would occur in a wild system and say, we're going to make some money on this. I mean, we don't have to go that far. We can talk about the deer right outside that fence over there. Okay? There's all this marvelous protein that's being created in this valley right now. We spend all our time and money figuring out ways to fence it out, make it go away, make it stop. Why not just eat it, folks? I'd soon eat the fawn over there as the broccoli. and that's where we need to get to understand that those systems are highly productive and that we need to move our thinking along a little bit on those issues.
Maybe one more question.
You said at the end you said that biodiversity or nature is not manageable or unmanageable. So how do you want to manage it to feed 10 million people in a few years?
Yeah, well, we're going to have to lose a lot of the people to begin with, but that's going to be taken care of. So that sounds pretty cynical, but I don't think it's that far off. I mean, people say, well, what's your solution from getting point A to point B? And, the industrial ag system is going to collapse under its own weight. It's not going to be pretty to watch. I mean, it already is collapsing. That's what we're watching. And so what I look for now are the ideas that are surrounding this that are going to percolate up after this. And they're going to percolate up in kind of an evolutionary fashion. You're not going to manage them. That's one of the lessons I hope we learned, that these solutions are ultimately local. They'll be driven by local evolution, and they will be driven to a certain degree by principles that we understand and a certain sense of humility and all that stuff that goes with it, that I hope goes. But is it going to be a clean, linear, managed process? Hell no, it's going to be a mess. Everything humans do is a mess. I mean, so that's the way it works. So how are we going to get there? How are we going to not get there?
Okay, one more.
So our entire energy infrastructure is also driven on photosynthesis, either millions of years old fossil photosynthesis or increasingly present day photosynthesis. I was just wondering what your thoughts are of how that's going to mix into this picture. As I think a lot of people think that the first order issue in climate change at least is finding energy that isn't fossil photosynthesis. So what do you see happening there, and where do you see the biggest problems being?
Well, agriculture comes into that on two levels. One is just the hydrocarbon use itself. Okay, so we talked about replacing nutrients in the soil because it depletes. Well, those nutrients are replaced with chemical fertilizers, which are based in natural gas. Okay, so we're converting natural gas to fertilizer. We're hydrocarbon energy to fertilizer. That's how we're doing it. Okay, and then we have the processing, transportation, all that stuff that goes on. So the astronomical increase in food prices we're seeing right now is being, in a huge part, driven by the increase in energy prices. That's going to have to decouple a certain amount of that energy intensity almost immediately. And that's what's happening. That's why these grass-fed beef guys are making a living, for instance, because the corn-fed beef is incredibly energy intensive. So they decoupled it, the market solution right off the bat. A primitive farmer uses something like a calorie of hydrocarbon energy, stored energy, fossil energy, to make 10 calories of food. A modern farmer reverses that and uses something like 10 calories of energy to make 1 calorie of food. So the obvious solution is how do we back off that? Very rapidly. And money will take care of that to a degree, but things like local food shed options. And, my favorite example of this was the Soviet Union when it collapsed and became Russia again. It had this incredible infrastructure of state-owned farms. Every bit as complex as ours, and in fact ours was modeled on the Soviet system. Literally, agronomists left the United States, went to the Soviet Union, studied it to invent industrial farming here. When it collapsed, everybody said, they're going to starve to death. Potato production in Russia increased with the collapse of the Soviet Union. It did indeed collapse on the farms. It increased in the cities. So people started growing potatoes in rooftop gardens and ended up growing more potatoes as a result of it by moving their agriculture local. People adapt. This is stuff we can do. We'll get there. But yeah, it's a huge thing. Now, the other level, of course, is what I talked about, and thing that is never, ever talked about, even to get it in print is very hard, and I've tried, believe me, is the fact that every cultivated field, including these politically correct cultivated fields, are exhaling carbon dioxide. Okay? And that is, a farmer in Iowa told me 2 weeks ago, he said, look, you can take the curve everybody takes of fossil fuel combustion through the Industrial Revolution to present and trace it with that carbon dioxide curve as everybody does. We've all seen those two curves together a million times. He says, take away the combustion curve, put back in the curve that says acres under the plow, tilled acres in the world. And it matches every bit as well. Every bit as well. So that's the other issue that needs to come up.
All right, well, thank you.
Thank you all. Enjoy Missoula.